Hello, this is, I don't know what homework this is, but it's a 30A video.
Homework 8.
Homework 8.
Thomas Brandt.
I'm Thomas Brandt. It's probably pretty smooth sailing once you know what you're doing. So we're given this, like, shape. The way I approached it was to split this into two different shapes. So we have this rectangle, and then we have this triangle. It's similar to, like, the problem we were doing in class with that, like, house-like shape. We're going to create a table. That's probably easiest. We're also given these values. And yeah, so we just set up some net force equations. This is how I calculated area. We have the centroid, the area, and then we multiply the two, and then we need the sums. Ultimately, we're looking for By, which you should get 57,416 pound-inches in the upward direction. And then for solving for the moment, I did net moment for B, and that should originally I got a negative of negative 2,348 pound-inches counterclockwise, but you can just change the sign and make it clockwise. Same thing.
So when you're calculating the moment, how did you do like the distances? Because like in my mind, I'm looking at it's like a bunch of arrows, or like when I first look at this, it looks like a bunch of force arrows. You know what I'm saying?
Yes. Well, for one, it's important to be consistent with your axis where you're setting x, y.
Yeah.
In that distance. That threw me off originally. In this case, it's the centroid values.
Yeah. Okay, yeah. Because you can assume that they're all going to be evenly distributed, and the centroid accounts for that, where the evenly distribution occurs.
Yeah. Like, don't look at this like, oh, I have to take the moment about each of these arrows. This is arbitrary. This amount, and you want to look towards the centroid.
I like
yeah,
that.
not too bad.
Yeah, thank you.
Do you know?
Oh yeah. Alright. My name's Case. I'm doing problem 2. So we have a shaded area in which we'll find the moment of inertia with respect to x. So that means we're going to use horizontal cross sections, and we're going to rewrite our equations in terms of x. So x equals, or in terms of y, sorry, as x equals equations, because we're integrating with respect to y. So we have our area as the top curve minus the bottom curve in terms of y, and we also can solve for m and k using our a and b like proportional values. So we have our moment of inertia is our area times y squared, which is like a cross-section part. And there's a lot of simplifications, but when we integrate from 0 to b, because we're doing with respect to the x-axis.
And usually with the x-axis, you always do horizontal, right? I think she said that in class.
Yeah.
It just makes it easier.
Because you could do the other way, but you'd have to use like...
It'd just be a lot difficult.
You have to do the parallel axis theorem.
Yeah.
But here we could just do this. Very easy calculation. I skipped a lot of steps, but like it's just like this integral, and once you solve for it and plug in your values, you get 1/20 ab squared, or ab cubed.
I think on mine I plugged in for my k and m values after integrating. I think it yields the same result. I mean, I don't know.
I just did that first because then you can cancel the a's and b's and
that makes,
get it in
that
terms
makes
of
more
just
sense
less variables.
But yeah, I think both work.
Yeah, both problems.
I think it's just an intuitive whatever.
Yeah.
Makes sense. Thank you.
Flipperoonie.
We'll get it up.
Yeah, that looks good.
Okay. So, hello, I'm Evan. For this problem, number 3, we are trying to determine the moment of inertia with respect to x and y. Kind of a crappy drawing I did here, but we basically have this upside-down T-shaped set of boxes, and the way we can approach this problem, we want to just keep it in rectangles. So we'll break this up into 2 separate rectangles, labeled 1 and 2. Yeah, that helps it out. Thank you. So the dimensions of this box will have 3.75 high and then 9 wide, and then for box 2, 6 high and 9 wide, or 3 wide, sorry. And we will approach this first by finding their centroids. So,
and that's using the parallel axis theorem. You need to find a centroid.
Yeah, but we'll get to that'll show up later. First, you'll actually recognize it from Thomas's problem. This is the same exact chart. It's just now we're doing it. I think his was with x values. We're doing y values here.
So we'll derive yi from just dividing the height by 2. And the area is simply the area of the box, 3.75 times 9. And we'll multiply those two values to get sorry, what is this? Do you know what this
tilde,
is?
y tilde.
Y tilde. We'll get y tilde times area. We'll get those for both blocks and then sum them. And then we will take 184.78 divided by 51.75 to get our
X bar, Y bar.
X bar. Well, we already had X bar, but now we can get Y bar.
So how did you have X bar?
That's just 9 divided by 3.
Because both shapes
Or
are
not,
even.
not 9 divided by 3, 9 divided by 2.
Yeah, because both shapes are evenly.
Yeah, exactly.
Perfect.
And so, I'll let you take over.
And that X is, that's just saying you don't have to calculate that sum, it's useless. And that's not like the variable X. The one in the sum.
Yeah, we don't need it.
Okay.
I'm just crossing it out.
So both, if it wasn't clear, both of the shapes have the same X tilde, so the X bar is going to be the same because they're both going to be like right here on this line. So it's pretty simple. But yeah, so you don't need a whole table. But yeah, so I'm going to do the actual inertia calculation. We kind of split this problem into 2 because there are only 3 problems. We have 4 of us. So for the inertia, your total inertia is going to be the inertia of one plus the inertia of the second one. So here, these are 2 things, and we're going to use the parallel axis theorem, which says for this specific inertia, we're going to have the inertia plus the area times d squared. And d squared is going to be the difference between where the local centroid and the global centroid is. So that's going to be your x bar minus x tilde. And the reason that we don't see that appearing right here is, so if you look at that, we don't have that value right here on the second part, because that's actually going to cancel out because the x tilde and the y x tilde and x bar, the global and local centroids, are the same, so they zero out. But then we go ahead and do this calculation. We're going to use the given formula, can be found in the textbook, for a rectangle. The inertia is 1/12 base height cubed. And then we're just going to go ahead and do that twice, perspective for x and y. And yeah, there you go. That's going to be your inertia. Is there any questions?
No, I get it.
All right.
I like that. Thank you.
I'm Andrew Thompson, if I didn't say so. Are we good?
Case John.
He's locked in, but yeah, okay. All right, bye-bye.